Hello everybody, I am Jitendra Singh and you are watching Physics and Travel. So today we are going to observe the motion of some bodies. So here I have a marker. So if you see, when I apply a force on it, it moves. Okay, and if something that I have a ball here, if I want to drop it from a height, but I am not giving any force to it, so it usually comes down. It usually comes down. So why it comes down? Because it is acted upon by gravitational force. Or I have a paper clip here and a magnet. So when the paper clip comes under the effect of magnet, so it is attracted by the magnetic field of the magnet. Now, these things we can infer a result that if anybody, whether it may be a marker or it may be a ball or it may be a paper clip or it may be a duster, so they need an external force to move. So is really they need external force to be continue in motion? So we are going to discuss about it. Okay, now you see the motion of these things. Now I have a marker over here. It is a round body and probably it has a less friction, so I can even move it with a blow of air. But something is there which moved this marker. So we reach a conclusion here. What is it? That if somebody is going to be in motion, that it needs to be acted upon by a force. This is rather looks like a very simple question, that everybody needs an external force to move. But you know, it took years to reach on this conclusion, but that also by Aristotle. You may have heard the name of Aristotle. He was a great Greek philosopher of his times, nearly 318 BC to 3. That if somebody moves, whether it moves in air or it moves on the surface, there is something that is continuously behind that object which pushes that body to move it further. Okay, but so this was the Aristotelian view, Aristotelian law, that everybody which is moving needs a force continuously which pushes from the body from back sides, that keeps the body moving. Then comes the observation of the Galileo. Galileo did some experiments with some inclined planes. So now I have two books over here. So let us make an inclined plane as formed by Galileo with the help of dusters. Okay. So now I am trying to move this ball from here. So this is an inclined plane downwards. This is the upward inclined plane. So here is some portion which is a little bit horizontal. So see the motion of the ball. I am starting here from the one end of the book. You see? So ultimately, it comes to rest after a moment. Why? Because there is a friction which resists its motion. Okay, when the ball moves from upward plane to down, so it accelerates. So it accelerates from the top of the book up to the center point, but it retards when it moves from this central point to upside. So every time it climbs up on the plane, it retards. So why? Resistance of friction. So see the motion. Okay. If the slope of the second plane is reduced, though I am replacing it with the marker. So now slope of the second plane is decreased. Now what will happen? The ball moves a little further. Now if the second plane is made horizontal, the ball may move indefinitely. If there is no friction, then the ball can move indefinitely up to infinite distance. So this has completely changed the Aristotelian view that every body needs a continuous external force to keep in motion, to be in motion. Under these ideas, which the laws we know today as Newtonian laws, they are formulated by Newton. Coming to the conclusion that according to Aristotle, we need external force for a body to be in a motion. But according to Galileo, he proved we don't need external force. But we need external force just to overcome the friction. In other words, if a body is under no external force, or you can say if external force is zero, the body will be in continuous motion, whether the body is at rest or the body is in motion. So it will continue to be in that state. So this was the basis of Newton's first law. And this is also called the law of inertia. So why? Because if external force is zero, this was called the law of inertia. So inertia is the resistance to change. Body does not change its position. A body does not change its state of rest or state of motion unless or otherwise it is acted upon by external force. So this was the basis of Newton's first law. So this is how Newton's first law of motions comes into effect, that every body continues to be in its original state, whether it is the state of rest or it is the state of motion, unless or otherwise it is external, it is acted upon by external force. Let us consider a simple case. We have a table and here is a book placed on this table, or you can say here is a body which is placed on this table. Now this body having some mass m is acted upon by gravitational force and its weight will be mg, which is downwards. But why is it not moving? Why it is not accelerating? Because the net force on this body is zero. Why? Gravitational force pulls it down, which is the weight of the body. Likewise, this table gives it equal reaction. So these reaction and the weight balances each other. So the net force on this body is balanced, is zero. So therefore this body does not accelerate. It keeps itself in state of rest. Now consider the motion of a car. So it picks up its speed in certain time, then it attains its uniform velocity, say 65 miles per hour. So then if it continues to be in 60 miles per hour, then the net force on this car will be 0, because the external force which is provided by the engine of the car is balanced by the resistive force of friction which is stopping it to move. So the net force is 0 because it continues to seem at same velocity. It moves with a constant velocity. It is under 0 external force. Okay. Now the concept of inertia is very much evident in our daily life experiences. Like if we are moving in a bus and bus is moving at constant speed, say 40 miles per hour, and if it suddenly the driver applies the brakes, then what happens? We generally fall forward. Why? Because the lower part of our body comes to rest with the floor of the bus, because the floor and our feet are attached with a force of friction, but the upper part of body is free to move. So as due to inertia, the upper part of body continues to be in motion due to inertia, so we fall forward. So like there is a case when suddenly the driver gears up the bus forward, so we generally fall backwards. So our feet moves with the bus, moves with the floor of the bus due to friction, but our upper part of body doesn't got ready to move with the bus, and due to inertia it wants to stay at rest, so it moves back. Newton's first law of motion, it was related to the simple cases when there is no acceleration, that change in velocity is 0. Either the body remains at rest or the body remains in uniform motion with no external force acting on the body. But Newton's second law of motion refers to the cases where there is a external force applying on the body continuously. Let us study a new called momentum. So what momentum is? Momentum is the product of mass of the body and velocity of the body. So this quantity is very important as far as the Newton's second law of motion is concerned. So its symbol is P, it's a vector quantity, and it is the product of mass and velocity of the body. Okay. Now let us study some cases of motion. So if we have one truck and one car, and both of have we know different masses. The car has a very less mass and the truck is heavier as compared to the car. So if we apply the same force on these bodies, no doubt the car gains velocity within a little time, but the truck will take some more time than car to take the similar velocity of car. So why? Because the mass of the truck is greater. So another example, if we drop two stones, one heavier and one smaller. So like if I throw this ball upwards, so you see I have applying the same force, but the smaller ball goes at more height than the heavier one. Okay. So same way, so this shows that mass plays an important role in motion. So heavier bodies has more mass. So if they have more mass, so definitely they will have more momentum. Now considering the case of velocities. Consider a case of a bullet. Bullet is very light, but when it is fired with a gun, it can make a casualty. It can kill a person. But if the same very bullet is thrown by our hand, So the same bullet doesn't harm anything. So this shows that the velocity of the bodies also plays an important role in the motion of bodies. So if the velocity is more, momentum of the body will be greater. Now coming to the third concept in momentum, which is not showing in this formula, it's the time. Suppose that cricket is played with this ball. Suppose that the batsman makes a shot for sixer and but failed to do so, and the ball becomes just short of the boundary, and a fielder there tries to catch the ball. And what he does, he suppose that I just try to throw this. So if I catch this like this, so I move my hands downwards, so making the time of impact longer. So then my hands will get a little jerk. But if I catch this ball like this, so ball gave me a greater jerk. Force will be felt little than if the time is shorter. So more important is that how fast the momentum changes. Now fourth thing, as the momentum is a vector quantity, so it must change with the direction. So consider a case when I suppose attach a ball with string and rotate it with a velocity v. So definitely at every point the ball changes its direction, so as its velocity. So if I want to rotate this ball more fast, then I need to apply more force. So more and more force needed if I rotate this body more fast, to a conclusion that momentum of a body changes with mass, with velocity, time, and with direction also. For the same change in momentum, if the time is less in which that momentum change is brought about for that change in momentum, it is concluded that the rate of change of momentum is directly proportional to the external force applied on the body, and the rate of change of momentum is directed towards the application of force. So this becomes our Newton's second law of motion, that dp upon dt is directly proportional to F external. So here P and F external both are vector quantities. As we have studied that P is the product of mass and velocity, so putting here F external is proportional to dp upon dt, or as the proportionality constant is 1 here, so we may put the value of P here as m times v. So as m doesn't change with time, therefore F external is equal to m d upon dt of v, or the rate of change of velocity, we may write it as acceleration. So this becomes the second form of Newton's second law of motion. So you may write it as F equal to dp upon dt, that is the rate of change of momentum is equal to the external force applied. Mind it, the force is external because the internal forces within the body, they tend to cancel each other. Okay. So or you may write it as F is equal to mass times acceleration of the body. The units of force can be written in the terms of mass and acceleration, as mass is measured in kilograms and acceleration is meter per second square. So the units can be written as Newton. So 1 Newton is kilogram meter per second square. And what about its dimensional formula? So likewise, the dimensional formula of F is mass and acceleration is LT minus 2. So it becomes MLT minus 2. There comes another interesting phenomena which is called impulse. Consider a batsman hitting a ball, or when we throw a ball towards a wall, it bounces back in just few seconds or in just a fraction of time. So if change in momentum takes place in a very short time, then this force is called impulsive force. Impulsive force. And we already have studied that F equal to dP upon dt. And if the force acts for a short time, force and time multiplies, and which gives us change in momentum. Similarly, according to this formula, if F is equal to dP upon dt, taking dt towards this side, we have dP again equal to F dt. So dt is a very small time. Change in momentum occurs for a short time with a force. Likewise, if it is a wall and we throw a ball towards this wall, it just touches and comes back, bounces back. So this force which the wall applies on the ball, it's a force which acts just for a short time, and change in momentum takes place. So this type of force is called impulsive force. Now coming to the Newton's third law of motion. If somebody, suppose we have a book placed on a table. So it is a book. So here is a table. This book, suppose it has a mass small m. It is at rest, or you may say it is in equilibrium at this position. Why? Because its weight, which is acting downwards, balanced by equal and opposite force which the top of the table applies on the book, and we call it a reaction. This reaction is equal to the weight of the body. Until it is equal to the weight of the body, till then this book will lie in equilibrium position. So every body which applies a force on another body is itself experience the same force in opposite direction. As if we slap somebody's face with our hand will experience the same force in reverse direction. So rather, it is not so hurting because the skin of our hand is hard as compared to the skin of the face of it. But always, if somebody applies a force on other body, it also experiences same magnitude of force but in opposite direction. So if F12 is the force on body 1 due to 2, then F12 will be equal to minus F21. So let us prove it. Okay, if first body, suppose this is body A, this is body B. Body A applies a force FBA on body B due to A. So dP, the change of momentum will take B upon dt equal to FBA, because according to Newton's second law of motion, the momentum change takes place of body B because A body is applying force on B. So likewise, this will be question number 1. If body B applies a force of FAB on A due to B, then it may be written as, so the momentum of body A will be changed due to the force FAB. So this may be equation number 2. Now adding 1 and 2, what we will get? dPB upon dt plus dPA upon dt equal to FBA plus FAB. So as these two forces are external forces, body A is experiencing force due to B, but body B is experiences force due to A. So both of these forces are external forces. So now if the external forces are 0, so if F external total is 0, then if F external is 0, then according to Newton's second law of motion, dP upon dt will be 0. Total momentum of the system will be 0, change in momentum. So therefore, FBA equal plus FAB will be 0. So if external forces are 0, this factor becomes 0 because there will be no change in momentum if external force is 0. Okay, so this factor gives us this thing, F12 equal to minus F21, or you can write it as FBA is equal to minus FAB. So Newton's third law is proved. As Newton's second law is F is equal to dP upon dt or MA. So these are two formulas of Newton's second law. So if external force, this thing, is 0, then MA tending to 0. So if external force is 0, M times A is 0. So mass of any body cannot be 0. Therefore, if this equality holds, then A is equal to 0. So what is it? If acceleration is 0, it means the body does not change its velocity. If the body is having a 0 velocity, then it will remain with 0 velocity. If it is moving at some constant velocity, it will remain with that constant velocity, but the acceleration will be 0. So this is nothing but Newton's first law. So in this way, first law of motion and Newton's third law of motion, starting from Newton's second law of motion. So here also we have started from Newton's second law of motion. So therefore, the only real law, the real law is Newton's second law of motion. So you may have encountered this question in your exams that show that Newton's second law is the real law of motion. So then what will you do? You will start from Newton's second law of motion, reach at Newton's third law. Again, you will start from Newton's second law of motion and reach at Newton's first law. The condition that will satisfy both is F external 0. So if you apply external force as 0, you will see that Newton's second law of motion is the real law of motion. We have studied Newton's first law of motion, which stated that every body continues in its original state of rest or of motion if it is acted upon by no external force. And Newton's second law, it includes the concept of momentum, that the rate of change of momentum of a body is directly proportional to the external force applied on the body, and the change in momentum takes place in a direction in which force is applied. And Newton's third law, to every action there is an equal and opposite reaction. So if we act on a body, that body also act to the first body. If we are standing on earth, our weight is downwards, then earth applies equal and opposite force, because weight is a force. Equal and opposite force towards upwards on our feet. So action and reaction both go same way. But action and reaction never cancel each other. So consider the case of the book. They will not cancel each other. Why? Because book is applying action on table, but table is applying action on book. They are not acting on same body. So action and reaction forces do not cancel each other. But the consequence of these action and reaction makes a body in equilibrium. But they do not cancel because they act on different bodies. If the both forces act on same body, then they cancel each other. But action and reaction never cancel each other. So I hope that all the laws of motion, Newton's first law, second law and third law, to make you understand. Thank you very much.